Yeah, we should be live. Let's just check that we're using the correct microphone. Yeah, that should be fine. Okay. So we're gonna be doing something different this time. We're gonna be reviewing a paper. Well, to be precise, ChatGPT 4.0 will be reviewing the paper. It's much smarter than we are, so hopefully I'll be able to contribute as well. Not a given, but yeah, I'll just start with a quick introduction to the paper. And yeah, this is acknowledgement as well, because we are mentioning the name. It's on screen and you will hear it when the robot is speaking.
The paper, titled Using Long Short-Term Memory, LSTM, Recurrent Neural Networks to Classify Unprocessed EEG for Seizure Prediction, by Jordan D. Chambers, Mark J. Cook, Anthony N. Burkett, and David B. Graydon, explores the application of LSTM neural networks to predict epileptic seizures directly from raw EEG data. Unlike traditional models that rely on feature engineering, this study tests whether LSTMs can process unprocessed intracranial EEG recordings for seizure prediction without the need for manually extracted features. It highlights promising results using the NeuroVista dataset, achieving predictions better than random and comparable to state-of-the-art models.
Yeah, so we'll see about that. I don't think they actually did a comparison to other models. I'm not sure. Another disclaimer, we haven't actually read the paper, so we did have a long discussion with ChatGPT before doing this video, so we discussed a few things, and we'll just go over go straight for it and go for the problems. We'll mention 10 problems with this paper, and then we'll go into the details. And eventually, ideally, we don't want to just be negative and talk about the problems. We will suggest some solutions as well.
Here's a quick list of problems with the paper. 1. Limited dataset generalizability. Reliance on the NeuroVista dataset limits applicability to other datasets, especially scalp EEG or different electrode configurations. 2. Patient variability. Model performance varies significantly across patients, with poor results for some, e.g. patient 6 and patient 15. 3. High false positives. Increased time in high raises the risk of excessive false alarms, reducing practical usability. 4. Overfitting concerns. The use of 80% of the data for training and reliance on a single dataset increase the risk of overfitting. 5. Reliance on long pre-ictal windows. The choice of 1 to 16 minutes for pre-ictal labeling may dilute seizure-specific features. 6. Lack of explainability. No in-depth analysis of what features the LSTM learns from the raw EEG data. 7. Comparison limitations. Comparisons with other models, e.g. CNN LSTM, critical slowing, are inconsistent due to differing evaluation metrics and labeling schemes. 8. Real-world applicability. No discussion of handling noise, real-time performance, or computational costs for clinical or wearable use cases. 9. Overemphasis on raw EEG. Assumes raw EEG is always better than pre-processed data without providing a direct comparison. 10. Insufficient discussion of limitations. Minimal discussion of practical and ethical challenges, such as user acceptance and psychological impact of false positives.
Right, well, that's a lot to take in. Yes, we'll go over those problems, issues with the paper one by one. But yeah, we just want to give it some context. Yes, one of the obvious things that stand out is, yeah, it seems like they only used one dataset, and potentially also use one way of processing. So LSTM model was the only one used in this study. There is supposedly, allegedly, no explanation of what the LSTM model actually learned. So there's supposedly no in-depth discussion of what features were actually used to make the predictions. But yeah, we'll go over those one by one in detail.
The paper relies exclusively on the NeuroVista dataset, which is widely used in seizure prediction research, but has inherent limitations. This dataset consists of long-term intracranial EEG recordings from a small group of 15 patients with focal epilepsy, which limits its representativeness of broader populations. For example, it does not include data from scalp EEG, different electrode configurations, or patients with generalized epilepsy. Additionally, 5 patients were excluded due to insufficient seizure counts, further reducing the sample size. This narrow focus raises concerns about the model's ability to generalize to other datasets, patient populations, or EEG recording setups, such as wearable devices or shorter-term monitoring systems.
Yeah, it's always suspicious when you see a patient 1 to 15, but then it goes 1 to 3, 6, 8, 9, 10, 11, 13, 15. So yeah, 5 of them are missing. Supposedly there was insufficient seizure count, but then, if you're using a model, I'm wondering why not just leave the data there. Well, I guess the rationale is that the different performance of different patients in terms of, so there's essentially different predictability level for different patients. Therefore, essentially smells of a bit of cherry picking, but yeah, let's just go over it, over all the 10 items, and then we'll go from there.
The model's performance varies significantly across patients, highlighting a key limitation in its ability to generalize effectively. While some patients, like patient 1 and patient 11, achieve high AUCs and sensitivity, others, such as patient 6 and patient 15, perform poorly, with low sensitivity and predictive accuracy. This variability may stem from differences in seizure patterns, EEG signal characteristics, or noise levels between patients. Such inconsistencies suggest that the model may not work universally and might require extensive patient-specific tuning, which is impractical in real-world scenarios. This limitation underscores the challenge of creating a one-size-fits-all seizure prediction model.
So ideally we would like, so either fine-tuning something for a specific patient, which is possible considering, these patients had an implant. There's not many of them, so you might as well fine-tune a model for a specific patient. I don't think it sounds too far-fetched. Again, considering there's only 15 of them, not too many events, at least for some of the patients that were even excluded from the data analysis. And then they also have an implant, so the recordings are long term. So it's definitely worthwhile doing machine learning and feeding, the results back into the model to try and improve it. And yes, eventually fine tune and optimize for a patient by patient basis.
The model often produces a high start time in high, which represents the proportion of time the model predicts a pre-ictal state. While higher sensitivity is achieved in some cases, this comes at the cost of frequent false positives. For example, in comparisons with the deep CNN and critical slowing models, the LSTM frequently showed increased time in high, such as for patient 1, where time in high rose from 0.08 in the critical slowing model to 0.42 when sensitivity was matched. Excessive false alarms can lead to reduced trust in the system, increased anxiety for users, and impracticality in real-world applications. This trade-off between sensitivity and false positives remains a critical issue for the model's deployment in clinical or wearable settings.
I'll just go over quickly over a few concepts just so we understand this dataset better, and then we go back. I'll quickly go over the comparison between a paradigm 1 and 2.
Paradigm 1 versus Paradigm 2, key differences and observations. Labeling scheme. Paradigm 1, preictal data is labeled as 1 to 16 minutes before a seizure, and interictal data as more than 16 minutes before a seizure. Paradigm 2, preictal data is labeled as 1 to 4 minutes before a seizure, and interictal data as more than 4 minutes before a seizure. Performance comparison. Paradigm 1 generally shows better AUC values for patients who benefit from longer preictal windows. E.g., patient 1 achieves 0.86 in Paradigm 1 versus 0.74 in Paradigm 2. Paradigm 2 performs better for patients who exhibit stronger predictive features closer to seizure onset. E.g., patient 6 improves from 0.63 in Paradigm 1 to 0.77 in Paradigm 2. Statistical significance. Patients like patient 1 and patient 13 show significant differences in performance between paradigms, as indicated by non-overlapping confidence intervals. For other patients, such as patient 2 and patient 9, the AUC values remain consistent between paradigms, suggesting robustness across different labeling schemes. Insights. Paradigm 1 provides a longer warning window, potentially useful for interventions requiring more preparation time, but it may dilute seizure-specific features. Paradigm 2 focuses on a shorter time frame closer to seizure onset, potentially capturing more precise preictal patterns but reducing the advance warning. Conclusion. The choice between Paradigm 1 and Paradigm 2 depends on patient-specific seizure dynamics and the required seizure prediction horizon. Paradigm 1 works better for some, while Paradigm 2 improves for others, emphasizing the need for personalized approaches.
Well, right. So there's definitely a need for personalized approaches. I think that's the biggest result of this study. However, so they have these two paradigms, right? So taking a different window size before the seizure actually occurred. So preictal is before you have epileptic activity in the EEG starts happening. So in this case, if we're going 16 minutes before a seizure, well, then we would definitely expect in the paper, once we train the model or the authors should have then, we expect for them to explain to us what is it in the signal that we start seeing a whopping 16 minutes before a seizure event. What is it in the signal that the model, currently this LSTM model, is actually detecting? What feature in this waveform is actually changing that we can essentially predict a seizure a whopping 16 minutes before it actually occurs? And yeah, we will see if it's actually is presented in the results of this paper. Spoiler alert, I don't think it is, but we will see. Yeah, and also quickly want to explain what time in high actually means.
Time in high refers to the proportion of time during which the model predicts a pre-ictal, seizure imminent state. It is an important metric for evaluating the practicality of seizure prediction systems. Why it matters. High sensitivity trade-off. Increasing sensitivity, true positive rate, often comes at the cost of increasing time in high, leading to more false positives. A model that spends too much time predicting a pre-ictal state may issue excessive false alarms, reducing its utility and increasing patient anxiety. Real-world implications. For practical seizure prediction systems, keeping time in high low is essential to avoid overwhelming users with constant warnings. Observations in the paper. The LSTM model generally has higher time in high than baseline models like the critical slowing model or the deep CNN model. For example, patient 1, critical slowing achieves a time in high of 0.08, while the LSTM when matched for sensitivity reaches 0.42, a significant increase. Patient 10, the LSTM improves sensitivity but increases time in high to 0.34, compared to 0.24 for the critical slowing model. Implications for the paper. While the LSTM achieves competitive or better sensitivity in many cases, its higher time in high suggests that it may generate too many false alarms. This reduces its reliability in real-world applications, where maintaining a balance between sensitivity and low false positives is crucial. Future work should focus on optimizing time in high to make the model more practical for clinical use.
Well, yeah, that's actually the main point. Is yes, that once you make the model essentially better, you increase its sensitivity, well, then you increase your false alarms as well. So that's all you need to know. It would be interesting to know if this was actually addressed in the paper. Yeah, that's just read the conclusion ourselves. LSTMs can classify and process EEG recordings. Okay, of course they can. You can, use essentially any algorithm on it. Question, is it useful? And it makes seizure predictions better than chance. Okay, better than chance. We can do better than chance. But they're talking about prediction, not detection. They haven't even. They could have been some seizures in this data set that weren't actually detected by this algorithm. So to begin with, you have to look at once you're talking about prediction, you actually have to mention detection as well. There could have been some seizures in this data set that went undetected, and maybe when you actually running a fancier algorithm on it, so essentially having a AI trying to detect those seizures, it might be actually detecting them when you didn't label them. So hopefully the dataset was labeled correctly. A lot of this data was home, I think it was home monitoring. So I don't know if they're just relying on all the events, that the device that the implant recorded on, or only the events that were, recorded in the hospital, while in that case another device would have been recording as well. So you're doing like a benchmarking to your, new device that is under study. Okay, maybe can we just repeat the conclusion of the paper? Can we do it verbatim?
Certainly. Here is the conclusion of the paper verbatim. LSTMs can classify unprocessed EEG recordings to make seizure predictions better than chance and comparable performance to the best models. This framework produces good performance when the experimental design was altered, without the need to reperform feature engineering or alter the model structure. This is a significant advancement on previous works. Our framework was developed using minimal data and transferred well to unseen data and unseen patients. Therefore, it is expected this framework will perform well on new datasets and could be applied to other classification problems.
Okay, there's many questions. When they say unseen, did they actually run the algorithm on unseen data in this study? Okay, let's go back to, yeah, we had this question section on potential overfitting. Yeah, we'll do that first.
The model's performance varies significantly across patients, highlighting a key limitation in its ability to generalize effectively. The model often produces a high time in high, which represents the proportion of time the model predicts a pre-ictal state. While higher sensitivity is achieved in some cases, this comes at the cost of frequent false positives. For example, in comparisons with the deep CNN and critical slowing models, the LSTM frequently showed increased time in high, such as for patient 1, where time in high rose from 0.08 in the critical slowing model to 0.42 when sensitivity was matched. Excessive false alarms can lead to reduced trust in the system, increased anxiety for users, and impracticality in real-world applications. This trade-off between sensitivity and false positives remains a critical issue for the model's deployment in clinical or wearable settings. The paper uses 80% of the dataset for training, leaving only 20% for testing. While this is a common split, it raises concerns about overfitting, particularly given the small dataset size, 10 patients after exclusions. Overfitting is further exacerbated by reusing the same dataset across multiple studies, limiting the ability to confirm the model's generalizability to unseen data. Although techniques like dropout are employed to mitigate this risk, the reliance on a single dataset with such a high training proportion makes it difficult to ensure that the model will perform well on new, real-world datasets with different characteristics. The paper's reliance on long pre-ictal windows, e.g., 1 to 16 minutes before a seizure in Paradigm 1, may dilute seizure-specific features critical for accurate predictions. While this approach captures a larger range of pre-ictal data, it potentially includes non-specific patterns or noise, reducing the model's sensitivity to the most relevant seizure-related changes. The drop in performance for some patients when switching to shorter pre-ictal windows, e.g., 1 to 4 minutes in Paradigm 2, highlights this issue. Additionally, using a fixed pre-ictal window across all patients ignores individual variability in seizure dynamics, which could require tailored labeling to optimize predictions. This rigidity limits the model's adaptability to diverse patient needs and seizure profiles.
So I don't quite understand the pre-ictal stage should be labeled. So that should be like the ground truth of this dataset. You should have ictal, non-ictal, and pre-ictal. So essentially it means seizure, no seizure, and just before seizure. So this just before seizure should be a predetermined a window, either based on hundreds of papers in the literature, relevant literature, or specific to these patients. So should have been labeled by an expert. So I don't quite understand the logic between the rationale behind just changing it from 16 minutes to 4 minutes. Except showing that yes, it's important what the pre-ictal window is considered to be. It's important for determining the model performance, because essentially they use the same model and just varied the pre-ictal window from 16 to 4 minutes, and in was it 3 or 4 cases it made a significant difference. Yeah, so the take-home messages are there's a high variability between patients, and then how the data is labeled makes a huge difference as well. So I'm not sure what to do with this results. Yeah, let's just keep going over the issues.
The LSTM model demonstrates promising performance, but its lack of explainability is a significant limitation. The paper does not provide sufficient insights into what features the LSTM is learning from the raw EEG data. While it suggests that the model might capture oscillatory peaks, trends, or information spread over multiple oscillations, these claims are not supported with detailed analysis or visualizations. This makes it difficult to interpret the model's decisions or validate whether it is leveraging clinically relevant features. Without explainability, clinicians may hesitate to trust or adopt the model, as they cannot understand the underlying basis for its predictions or ensure its robustness across varying conditions.
Well, yeah, that's the main sticking point.
The paper's comparisons with other models, such as the deep CNN and critical slowing models, are limited due to differences in evaluation methods and experimental setups. For instance, 1. Labeling schemes. The LSTM model defines pre-ictal windows differently from some baseline models, e.g. 1 to 16 minutes in Paradigm 1 versus 1 to 4 minutes in Paradigm 2. This inconsistency makes direct performance comparisons challenging. 2. Sensitivity metrics. The critical slowing model considers a single correct prediction during the pre-ictal period sufficient, while the LSTM requires all pre-ictal samples to be classified correctly. This stricter criterion may unfairly penalize the LSTM in comparisons. 3. Feature engineering. Baseline models often use pre-processed or feature-engineered data. e.g., frequency domain transformations, while the LSTM uses raw EEG. The lack of direct comparisons between raw and processed EEG further complicates the evaluation. These differences highlight the need for standardized benchmarks and evaluation frameworks in seizure prediction research to ensure fair and meaningful comparisons.
Yes, just a comment on the labeling schemes. Yeah, you could essentially make another model fail if you change your labeling definitions, because that meant to be your ground truth. So in this case, you could have taken another model and done the opposite, and it will be performing better with the 4-minute pre-ictal window versus the 16, and it will show you like an opposite effect potentially to what we see in these results. Yeah, I'm also not quite sure what's unique about LSTM in terms of using raw EEG. Is it a thing, or could you, I assume you could use LSTM on any feature engineering extracted from the raw data? Why did you have to use it on raw EEG specifically? And I assume in the paper they didn't actually compare it to using it on features of the EEG signal rather than the raw EEG. So I'm not sure why they're making comments on it to begin with.
The paper's focus on offline evaluation highlights several limitations in terms of real-world applicability. 1. Handling noise and artifacts. The model processes raw EEG data, but real-world recordings, particularly from wearable or scalp devices, are prone to noise, artifacts, and signal dropouts. The study does not address how these challenges would impact predictions or propose mitigation strategies. 2. Real-time performance. While the model is tested on pre-segmented data, real-world applications require continuous data streaming and prediction. The computational requirements for LSTMs, especially with large EEG datasets, might hinder deployment on edge devices or in clinical environments without further optimization. 3. Balancing false positives. High time and high rates could overwhelm users with frequent false alarms, leading to frustration and reduced trust in the system. Real-world implementations would need mechanisms to manage this trade-off. 4. Patient-specific tuning. The model's variable performance across patients suggests that personalization is necessary. However, the paper does not explore how this tuning could be efficiently implemented in clinical or wearable scenarios. 5. Practical usability. The psychological and practical impact of seizure warnings, especially frequent false positives, is not discussed. Real-world systems must consider user experience, including minimizing anxiety and providing actionable insights. Addressing these issues is critical for transitioning from research to clinical or wearable applications. The paper's emphasis on processing raw EEG data without feature engineering, while innovative, introduces some challenges. 1. Potential loss of robustness. Raw EEG often contains noise, artifacts, and irrelevant information. Pre-processing steps, like filtering or artifact removal, can enhance signal quality and focus on clinically relevant features. The paper does not compare the performance of raw EEG with pre-processed data to validate the superiority of this approach. 2. Computational inefficiency. Processing raw EEG directly requires more computational resources, as the model must learn to extract features internally. This can increase training time and make real-time applications more challenging, especially on edge devices. 3. Overlooking established methods. Feature engineering, such as time frequency analysis or autocorrelation, has been shown to improve seizure prediction in many studies. The paper assumes raw EEG inherently contains all the necessary information, but does not explore whether combining pre-processing with LSTMs could yield better results. 4. Data variability. Raw EEG data can vary significantly between patients, devices, and recording conditions. Pre-processing often normalizes these differences, which might improve model generalization across datasets and patient populations. While the focus on raw EEG highlights the LSTM's capability for automated feature learning, the absence of a direct comparison with pre-processed EEG leaves the question open as to whether this approach truly offers an advantage.
Yeah, I want to talk about this one. So yes, so over reliance on raw EEG. Yeah, so ideally, when you run the model, then eventually it should have told you which features are used. So you could do like a parameter reduction and see which features are mostly used to make the decision, and then actually go back and say, you know, how you should have pre-processed the data like next time. Because so say if this is your only data, and I think this will be the only data for this data set, that the implant is not available anymore. This is probably also something the authors forgot to mention. So this is a very unique data set from an implantable device from a company that does not exist anymore. So for it to be actually useful, we should have actually specified what features are important. You know, if we did an LSTM, then show which features, and then later we could then say that if we pre-processing the dataset to extract specific features from the raw EEG data, future models can have better performance. But I'm not sure if this is what the aim of this paper was. Maybe the robot can comment on that.
The paper provides minimal discussion of its limitations, which undermines its practical and scientific implications. Key overlooked aspects include 1. Dataset limitations, the exclusive use of the NeuroVista dataset and the exclusion of certain patients due to low seizure counts limit the model's generalizability. This is acknowledged briefly but not explored in detail. 2. Patient variability. The inconsistent performance across patients is noted in results but not discussed as a potential obstacle to widespread clinical adoption. The need for patient-specific tuning is not addressed sufficiently. 3. Real-world challenges. Issues such as noise, artifacts, and real-time implementation are not mentioned. The paper assumes the model would perform similarly in clinical or wearable scenarios without evidence to support this claim. 4. False positives and user experience. High time and high rates could lead to frequent false alarms, negatively affecting user trust and mental health. The potential psychological impact of these predictions on patients is not considered. 5. Computational requirements. The high computational cost of training LSTMs is briefly mentioned, but the challenges of deploying such models on resource-limited devices are not discussed. 6. Ethical and practical considerations. The authors do not address how seizure warnings might be integrated into clinical workflows or whether patients and caregivers would find such predictions useful or burdensome. By failing to delve into these limitations, the paper leaves critical questions unanswered about the model's readiness for real-world application and its impact on patients and clinicians.
Yeah, there's a lot to take in. just go over a few questions that we should be asking regarding this paper results study.
Here are some questions about the paper for you to consider. 1. Dataset. Do you think relying exclusively on the NeuroVista dataset is justified, or should the authors have tested their model on additional datasets to improve generalizability? How would you approach evaluating the model on scalp EEG data or other publicly available datasets? 2. Patient variability. What factors do you think contribute to the inconsistent performance across patients, e.g., EEG patterns, noise, seizure variability? Would you suggest incorporating patient-specific tuning into the model, or is a generalized approach preferable for practical applications? 3. Feature engineering. While the paper avoids feature engineering, do you think combining pre-processing, e.g., artifact removal, bandpass filtering, with raw EEG analysis might improve performance? Could a hybrid model, combining traditional features with LSTM processing, strike a better balance between efficiency and accuracy? 4. Explainability. How important is model interpretability for clinical adoption in seizure prediction? What methods could the authors use to better explain what the LSTM is learning from the EEG data? For example, would attention mechanisms or feature visualization help? 5. False positives and real-world impact. The high rate of false positives could lead to user frustration. What thresholds or mechanisms would you suggest to minimize this while maintaining sensitivity? Do you think the psychological impact of false alarms on patients and caregivers should be studied alongside technical performance? Model adaptability. The paper suggests the model could adapt to different seizure prediction horizons. How would you validate this adaptability for individual patients? Could this framework be modified to predict generalized seizures or non-epileptic events? 7. Clinical applications. If you were tasked with deploying this model in a real-world clinical or wearable setting, what additional steps or modifications would you prioritize? Do you think the computational requirements of the LSTM model are realistic for portable or real-time applications? 8. Ethical considerations. Should the authors have addressed the ethical implications of deploying seizure prediction systems, such as false assurances or patient anxiety? How would you balance the model's potential benefits against these risks? Your expertise in EEG and epilepsy could
Yes, so there's a couple of comments on that. So if you can actually find the details about the NeuroVista dataset, how many times it was used in research, when the data was recorded, and most importantly, does this specific device still exists or not? So I understand that this particular paper is focused on this data set, and that's fine. But yes, it's obviously a problem that there was no comparison to anything else. But yes, essentially the idea is, because this is a unique data set that probably, correct me if I'm wrong, would not be repeated, then yeah, we would like to extract as much information as possible from it and learn as much as possible about training new models on new data. So yes, whatever model was, developed here should have been tested on a different data set and compared. I think that wasn't done in this study, but correct me if I'm wrong. Yes, if we're going this pathway of implantable devices for monitoring seizures, yeah, patient-specific tuning makes a lot of sense because it's an implant, you don't have too many patients. Then you're recording long term as well, so you do wanna, maximize performance. So yes, tuning your model on the specific patient data sounds to me like a no-brainer. What do you think? Yeah, the feature engineering again from this dataset, another thing that I don't think that was done properly is you actually have to show what the model have learned, and then you could extract these features from future datasets. Data sets. What do you think?
Your comments touch on several critical points. 1. Labeling schemes and ground truth. You're absolutely right that the choice of labeling schemes significantly influences model performance. Labeling definitions essentially create the ground truth, and changing these can make or break a model. For instance, if you designed a different model optimized for shorter preictal windows, it might outperform the LSTM on the 1 4-minute labeling scheme, but fail on the 1 to 16-minute window. This highlights how subjective labeling decisions can skew results and complicates fair comparisons between models. 2. Uniqueness of LSTM with raw EEG. The paper does not convincingly establish why LSTMs are uniquely suited for raw EEG data. While LSTMs excel at processing sequential data, there's no inherent reason why they couldn't also be applied to feature-engineered inputs. For example, frequency domain transformations, autocorrelations, or spectral features could still leverage LSTM's temporal modeling capabilities. The authors missed an opportunity to compare the performance of the LSTM on raw EEG versus preprocessed or feature-engineered data. 3. Comparison to feature-engineered models. The lack of comparison with feature-engineered EEG signals is a glaring omission. Without such a comparison, it's unclear if using raw EEG offers any tangible advantage beyond avoiding the labor of feature extraction. Using raw data is a novel angle, but it doesn't automatically make it superior unless it provides demonstrable improvements in accuracy, robustness, or adaptability. Your critique underscores a core issue in the paper. While the authors propose that processing raw EEG with LSTMs is advantageous, they fail to prove this assumption. Comparing the model to feature-engineered approaches or hybrid methods could have clarified whether the novelty of their approach translates into practical benefits.
Okay, but don't just to critique the paper for the sake of it, but I really just genuinely don't understand the choice of a specific model and a specific data. So an LSTM is one model out of hundreds or thousands. What do you think? And also the use of raw EEG is also quite unusual as well. Normally you'll be looking at some features in addition to the raw EEG, or just looking at the raw EEG. So yeah, if you can share your ideas, that would be great.
Your insights are spot on and highlight a missed opportunity in the paper. Here's a breakdown of your key points and some additional commentary. 1. Over-reliance on raw EEG. While using raw EEG avoids feature engineering, it doesn't help future studies refine data collection or pre-processing practices. Ideally, the LSTM model could have been analyzed post hoc to identify which aspects of the signal, e.g., frequency bands, amplitude variations, or specific patterns, were most predictive of seizures. By not performing a feature importance analysis, the study misses the chance to inform better pre-processing techniques for future models. For example, if the model predominantly uses low-frequency components, pre-processing could filter out irrelevant high-frequency noise in subsequent studies, improving model efficiency and robustness. 2. Parameter reduction and feature extraction. LSTMs could have been leveraged to identify the most critical features through techniques like saliency maps, attention mechanisms, or sensitivity analyses. This information could have been used to reduce the dimensionality of the data and guide pre-processing strategies. The failure to do so leaves an open question about whether pre-processing, e.g., bandpass filtering or extracting power spectral density, might outperform raw EEG processing. 3. Uniqueness of the dataset. The NeuroVista dataset is indeed rare and valuable, especially as the implantable device is no longer available. This makes it even more important to maximize the utility of the dataset by identifying transferable insights, such as which features are critical for seizure prediction. If no new data of this kind will be collected, future models will rely on these findings to inform pre-processing strategies for other types of EEG data, such as scalp recordings or different implantable systems. 4. Purpose of the paper. If the paper's aim was purely to demonstrate that raw EEG can be processed without feature engineering, it partially achieves that goal. However, as you suggest, this isn't the most practical or forward-thinking approach. A more impactful aim would have been to explore whether using raw EEG adds value over pre-processed data and to identify what specific features contribute to predictions. This would make the findings more actionable for future research and development. Comment on the paper's aim. It seems the paper aimed to show that LSTMs can handle raw EEG effectively, avoiding the manual labor of feature engineering. However, this approach feels short-sighted given the uniqueness of the dataset. While it demonstrates a novel method, it doesn't maximize the dataset's potential for broader utility. The next logical step would be to extract insights from the LSTM's performance to guide pre-processing strategies for future work, particularly if future studies won't have access to similarly high-quality data. In summary, the paper might have benefited from balancing novelty with practicality, showing not only that LSTMs work on raw EEG, but also how this knowledge can be applied to improve future seizure prediction models. You're absolutely right on several counts, and I agree with your analysis. Here's a response addressing your points. 1. Details about the NeuroVista dataset. The NeuroVista dataset has been extensively used in seizure prediction research, largely because it provides long-term intracranial EEG recordings. It was recorded between 2010 and 2013 as part of a clinical trial using an implantable seizure advisory device. Unfortunately, the NeuroVista company no longer exists, and the device is not available, making this dataset irreplaceable. This uniqueness adds to the urgency of extracting as much useful information as possible from it. Despite its widespread use, the dataset's focus on focal epilepsy and intracranial recordings limits its generalizability to other types of epilepsy or EEG systems, such as scalp EEG or newer implants. 2. Missed opportunity for broader insights. As you pointed out, because this dataset is unlikely to be replicated, the study should have focused not just on proving the feasibility of raw EEG processing, but also on extracting transferable insights, showing what the LSTM model has learned, e.g. through saliency maps or sensitivity analysis, would allow researchers to identify critical features and refine future pre-processing steps. This is especially crucial if future data comes from different devices or less invasive systems. Testing the LSTM model on another dataset, such as scalp EEG or a smaller-scale intracranial EEG dataset, would also have provided insights into how well the method generalizes. 3. Patient-specific tuning. I fully agree that patient-specific tuning is essential for implantable devices. Each patient's seizure patterns, EEG characteristics, and brain dynamics are unique, and implantable devices provide the stability and long-term data needed for personalized models. Patient-specific tuning is not only practical, but also a no-brainer, as it maximizes performance while minimizing false positives or missed seizures. The long-term, continuous nature of implantable device recordings makes them ideal for adaptive or fine-tuned machine learning models. 4. Feature engineering from learned features. You're absolutely correct that a key outcome of using a unique dataset like this should be identifying what the model has learned. This could be done through techniques like feature importance ranking or visualizing the input-output relationships within the LSTM. Once identified, these features could be explicitly extracted and used in future datasets to build simpler, more interpretable models that don't require raw EEG processing. For example, if the LSTM heavily relies on specific frequency bands or amplitude modulations, future work could focus on those features to improve efficiency and accuracy. New 5. Missed comparisons. You're right that the study should have compared the LSTM's performance on the NeuroVista dataset with other datasets or feature-engineered approaches. Without such comparisons, it's hard to assess whether the raw EEG method is truly superior or just convenient for this particular dataset. The absence of external validation limits the conclusions and the model's applicability to real-world scenarios or other datasets. Summary. Your comments highlight the core issues. While the NeuroVista dataset is unique and valuable, the study misses the opportunity to extract broader insights that could benefit future research. Patient-specific tuning is indeed critical for implantable devices, and showing what the model has learned would have been a major step forward in making the results transferable. Finally, comparing the LSTM to other datasets or approaches would have strengthened the conclusions and improved the study's real-world relevance.
Yeah, I don't quite understand. They have a figure where they mention. Oh, okay. Those are the time information is essentially from different studies. So these 9 parameters are being imported from different studies, from different data processing of the same dataset. Is that correct, or I missed something? So essentially the only parameter they looked at in this study is that 4 or 16-minute difference of before seizure time period. Is that correct, or please also don't tell me that that you agree with me. I don't think you are an agent yet, so you can not agree or disagree. Let's establish that.
You raise a critical point, and I think it's worth breaking this down into 2 parts: the choice of LSTM as a model and the use of raw EEG data. Both decisions are somewhat unusual in the broader context of EEG-based seizure prediction research, so let's unpack them. 1. Why LSTM? Strengths of LSTMs. LSTMs are a type of recurrent neural network designed to process sequential data, making them well suited for time series data like EEG. They address the vanishing gradient problem, which allows them to capture long-term dependencies in sequential data, something critical for EEG signals where temporal patterns often span seconds to minutes. However, this property isn't unique to LSTMs. Other models, such as temporal convolutional networks, TCNs, or attention-based transformers, can also capture long-range dependencies. Choice justification. It's unclear why the authors chose LSTM specifically. They don't compare its performance to other models, such as convolutional neural networks, CNNs, or hybrid architectures like CNN LSTMs. A CNN, for instance, could have extracted spatial and temporal features from EEG data effectively and may have been computationally more efficient. The decision to use LSTM might stem from its strong track record in sequential data processing, but this feels like a default choice rather than one backed by exploration of alternatives. Broader context, with the vast range of models available, transformers, TCNs, etc., the authors didn't justify why LSTM was ideal for this dataset or problem. It's worth questioning whether the same results could have been achieved or improved with a simpler or more interpretable model. Why use raw EEG? Advantages claimed. The authors argue that processing raw EEG avoids feature engineering, a labor-intensive step that might restrict the model to specific human-defined features. This lets the LSTM discover the relevant patterns or dependencies in the data without preconceptions. In theory, this is an interesting approach because EEG signals are complex and may contain subtle features that manual feature engineering could miss. Challenges and unusual aspects. Most EEG-based models rely on features like power spectral density, frequency bands, delta, theta, etc., or autocorrelation, because these are well-established correlates of brain activity and seizures. Ignoring these entirely puts a significant burden on the model to extract meaningful information from raw, noisy data. Raw EEG can contain artifacts, e.g., motion, eye blinks, or electrical interference, that might not contribute to predictions but could confuse the model. Pre-processing steps like artifact removal and filtering are standard in EEG research, but appear to have been bypassed here. Missed opportunity. The authors could have compared the performance of the LSTM on raw EEG versus pre-processed or feature-engineered EEG. This would have shown whether using raw data truly adds value or simply shifts the burden from pre-processing to computational complexity. Hybrid approaches, where the model is fed both raw EEG and engineered features, might have struck a better balance between leveraging the richness of the raw signal and incorporating domain knowledge. Unusual approach. Using raw EEG is atypical because most studies aim to reduce the dimensionality and noise in the signal to make it more manageable for machine learning. While the authors argue this is an advantage, they don't convincingly show that raw EEG outperforms traditional feature-engineered data. My ideas and suggestions. Model choice. LSTMs are a solid choice for sequential data, but are far from the only option. Exploring models like CNN LSTMs, TCNs, or transformers might yield better results, especially for datasets with long recording durations. Simpler models, like random forests or gradient-boosted trees on feature-engineered data, could serve as a baseline to demonstrate whether the LSTM truly adds value. Raw versus pre-processed EEG. Testing the LSTM on both raw and pre-processed EEG would clarify whether using raw data is advantageous. This comparison could involve standard EEG features, e.g., power in different frequency bands, or even a mix of raw and engineered features. Analyzing what the LSTM learns from raw EEG, e.g., through saliency maps or attention mechanisms, could guide pre-processing strategies for future studies. Hybrid approaches. Combining raw EEG with feature-engineered inputs might allow the model to leverage both raw signal richness and domain-specific insights. For example, feeding the LSTM both time domain features, raw EEG, and frequency domain features could improve performance and interpretability. Patient-specific models. Since seizure patterns and EEG characteristics vary greatly between individuals, patient-specific models make sense, especially for long-term implantable devices. Training models on individual patients' data would maximize predictive accuracy and reduce false positives, making the system more practical in clinical settings. Final thoughts. The choice of LSTM and raw EEG seems driven more by novelty than by a clear demonstration of superiority over other methods. While these choices are valid, the paper doesn't sufficiently justify them or explore alternatives. A more comprehensive study comparing models and pre-processing strategies could clarify whether LSTMs and raw EEG truly represent the best approach for seizure prediction, or simply one of many possibilities. What do you think about these suggestions? You're absolutely right to ask for clarity, and let me focus on addressing the points directly without adding subjective agreement. 1. Driving information from 9 parameters. The 9 parameters in the figure are time-related features derived from prior studies on the same NeuroVista dataset. These include parameters like hour of the day of the week, and log time since the last seizure, among others. These features are external to the raw EEG data and represent an additional layer of input to the LSTM. They are essentially metadata that reflects seizure cycles or periodicities, which other studies have found to be predictive. However, these parameters were not derived from the EEG itself in this study. Instead, they were carried over from prior work and combined with the LSTM outputs as part of the dense classifier. Time labels as the main experimental parameter. Yes, the primary experimental variable studied here was the time labeling of pre-ictal versus interictal EEG segments. Paradigm 1 used a 1 to 16 minute pre-ictal window. Paradigm 2 used a 1 to 4 minute pre-ictal window. Beyond this, the study doesn't appear to explore additional parameters or alternative methods of segmenting pre-ictal and interictal data. 3. Scope of parameter exploration. If you're asking whether they tested other features derived from the raw EEG, like frequency bands, power spectral density, or autocorrelation, they didn't. The study focuses heavily on comparing different pre-ictal window lengths and combines the LSTM's raw EEG outputs with the 9 time-related parameters to refine predictions. But it does not explore additional EEG-derived features or their impact. Does this align with your interpretation? Or is there something more specific you'd like to clarify?
Yeah, there's a lot of weird things about it. And now that I'm looking at it in more detail, yeah, there's this essentially 50 seconds before of data. Is it ictal? It looks like before seizure. Is that correct? In figure 1. Can you explain it in more detail? And how does it relate to the 4 versus 16 minutes? Interictal window that was mentioned elsewhere. It's actually quite important, so
You're absolutely correct that the figure, particularly the 5 LSTM models processing 10-second segments, introduces some confusion when compared to the time windows described elsewhere in the paper. Let's break this down in detail. What Figure 1 shows? 1. Input to each LSTM model. The model processes 1-minute EEG segments split into 5 non-overlapping 10-second chunks. Each of these 10-second segments is fed into a separate LSTM instance, which outputs predictions. 2. LSTM outputs combined. The outputs from these 5 LSTM models are then aggregated to produce predictions for that 1-minute segment. This aggregation is combined with the time information, the 9 external parameters, in the dense classifier. 3. Temporal range. Since the 1-minute segment represents data directly preceding the seizure or during interictal periods, the LSTM models essentially predict based on sh52 seconds, technically 50 seconds if strictly summed, of EEG activity. Relation to the 4 and 16-minute windows. 1. Paradigms mentioned in the paper. Paradigm 1, 1 to 16 minutes. Data within 16 minutes before the seizure is labeled as preictal. Data beyond 16 minutes is labeled as interictal. Paradigm 2, 1 to 4 minutes. Data within 4 minutes before the seizure is labeled as preictal, and anything beyond that is interictal. 2. Conflict or misalignment. The LSTM model itself only analyzes 1-minute chunks broken into 5 10-second pieces, which seems disconnected from the longer time horizons, 4 minutes or 16 minutes, mentioned in the paradigms. It appears that the classification, preictal or interictal, is based on whether the entire 1-minute segment falls within the defined preictal window, e.g., 1 16 minutes or 1 to 4 minutes. However, the figure doesn't explicitly clarify how the preictal and interictal labels are assigned to these smaller 1-minute segments. For example, does each 1-minute segment only get a label based on its midpoint? What happens to segments that partially overlap the preictal window? Key issues and ambiguities. 1. Temporal context limitations. Although the LSTMs analyze sequential data, the temporal resolution is confined to 10-second chunks, and no explicit mechanism ensures that these predictions are influenced by longer-term trends, e.g., 4 or 16 minutes. This contradicts the claim that the LSTM leverages longer preictal time windows since the actual data input to each LSTM model is much shorter. 2. Lack of explanation. The paper does not clarify how the 1-minute segment predictions relate to the larger time windows described in paradigms 1 and 2. For instance, it's unclear how predictions for 1-minute segments are aligned with the 4 or 16-minute definitions of preictal and interictal periods. 3. Potential oversights. The model seems to assume that all the information needed for classification is present in these 10-second segments, which may not fully capture the broader dynamics of seizures. The longer preictal windows described in paradigms 1 and 2 are only considered during labeling, not in the actual processing of the data. Summary of how it relates. The 1-minute segments are labeled as preictal or interictal based on whether they fall within the 4 or 16-minute preictal windows. However, the LSTM models themselves process much shorter 10-second chunks, and the figure doesn't clearly explain how these smaller chunks capture the dynamics of the longer windows. This mismatch between the time windows described in the paradigms and the short-term focus of the LSTM processing is a potential flaw, or at least a point of confusion in the study. Does this address your concerns, or is there a specific aspect you'd like clarified further?
yeah, I don't know about that. Yeah, there seemed to be a confusion. Yeah, it's super confusing. Yeah, I was just thinking it's not a great study whatsoever. It's funny that they mentioned like unprocessed EEG, but then there seemed to be a lot of processing on the time scale of things. Yeah, there's a lot of selection of which time window to look at. If it's 10 seconds, 5 times 10 seconds. If it's 4 minutes, then 16 minutes. Mentioned it doesn't seem to be included in the processing, but yeah, I'm just really confused. But yeah, that's okay. If we can just finalize this review and do like a general overview of what we discussed, and also, yeah, if you could touch on what do you think? Did the paper, the results, and the method actually addressed why specifically LSTM is used in this case, and why we're using raw EEG instead of feature extraction. So in these terms, if you can give a critical summary, we will be happy, and we could finish the review. We might be actually writing a blog on it, but I'm not sure yet. What do you think?
Let's finalize this review with a critical summary and a general overview of the paper, touching on all the points of confusion and critique we've discussed. I'll also address whether the results and methods justify the use of LSTM and raw EEG. Critical summary of the paper. Strengths. 1. Novel approach. The idea of using LSTMs to process raw EEG data without feature engineering is innovative, aligning with the goal of removing human bias in selecting features. 2. Unique dataset. The use of the NeuroVista dataset, a rare long-term intracranial EEG dataset, adds value. This dataset's historical significance makes any insights gained from it potentially impactful. Weaknesses and points of critique. 1. Confusion in the temporal design. The study claims to analyze raw EEG, but introduces significant timescale processing complexities. 10-second EEG segments processed by LSTMs are combined into 1-minute outputs. These outputs are then labeled as pre-ictal or inter-ictal based on paradigms using 4 or 16-minute windows. This multi-level temporal design introduces ambiguity and makes it unclear how much of the broader seizure dynamics are captured. For example, why were 10-second segments chosen, and how do these short segments relate to longer seizure cycles? The connection between the pre-ictal definitions, 4 or 16 minutes, and the LSTM predictions is poorly explained, leaving the impression of a disjointed framework. 2. Overemphasis on raw EEG. While the paper markets itself as focusing on unprocessed EEG, it relies heavily on external metadata, e.g. the 9 time-related parameters. This combination dilutes the claim of raw EEG-only analysis. Furthermore, there's no comparison of using raw EEG versus engineered features, leaving a critical gap in the evaluation of the model's design. The lack of analysis on what features the LSTM might have learned undermines the ability to interpret or refine future pre-processing pipelines. 3. Method justification is weak. The authors fail to justify why LSTMs were chosen over other models like CNNs, CNN LSTMs, or attention-based transformers, all of which could handle sequential EEG data effectively. There's no exploration of whether LSTMs on raw EEG outperform simpler methods, e.g. feature-based classifiers, on the same dataset. 4. Dataset-specific limitations. The NeuroVista dataset is valuable but unique and unrepeatable, given the device is no longer manufactured. The authors missed an opportunity to extract and analyze reusable features for future work. The study doesn't test the model on other datasets, limiting its generalizability. This is critical for demonstrating the robustness of the method. 5. Poor interpretability. The paper does not provide insights into what the LSTM learned from the raw EEG data. This is a missed opportunity for parameter reduction, which could have informed better pre-processing strategies for future studies. 6. Real-world relevance. While patient-specific tuning is mentioned as an advantage of LSTMs, the study does not adequately demonstrate how this could be implemented in practice. Summary of results and method. Did they justify their choices? Tox 1. Why LSTM? The paper does not convincingly justify its choice of LSTMs over other models. LSTMs are appropriate for sequential data, but are not unique in this regard, and their computational complexity might outweigh their benefits in this study. Without comparing LSTM performance to simpler or alternative models, it's unclear whether the use of LSTMs was necessary or optimal. 2. Why raw EEG? The justification for using raw EEG is similarly weak. The authors claim to avoid feature engineering, but the reliance on metadata, 9 time-related parameters, complicates this claim. Without comparing raw EEG to feature-engineered data, the decision to focus on raw EEG remains speculative. The lack of interpretability means we don't know if the model extracted meaningful features or simply overfit noise in the data. General overview of our discussion. 1. Strengths. The study explores an innovative approach to EEG processing using raw data and advanced sequential models like LSTMs. The unique NeuroVista dataset provides a rare opportunity to analyze long-term intracranial EEG data. 2. Weaknesses. The paper's methodology is convoluted, especially regarding temporal windows, and introduces unnecessary complexity. There is no proper justification for key design choices, such as LSTMs or raw EEG. The lack of comparative analysis, either to other models or pre-processing approaches, limits the broader relevance of the results. The findings remain dataset specific and do not generalize to other datasets or practical scenarios. 3. Unanswered questions. What specific features of the EEG signal were driving the predictions? Could the model perform better with pre-processed data or feature engineering? How does this framework compare to existing state-of-the-art models in terms of performance and interpretability? How do the 10-second LSTM outputs reflect seizure dynamics in longer pre-ictal windows, e.g. 4 or 16 minutes? Concluding critical remarks. While the paper provides an interesting take on seizure prediction with LSTMs and raw EEG, it ultimately falls short of delivering a clear, robust framework. The methods lack transparency, the design choices are poorly justified, and the results are not benchmarked against alternatives. These limitations make it difficult to assess the true contribution of this work to the field. The over-reliance on a unique dataset without extracting reusable insights further diminishes its impact. Future studies should focus on comparing pre-processing strategies, exploring alternative models, and emphasizing interpretability to ensure that their findings are both generalizable and actionable.
The main question about the studies like this in general. In this study, they only mention prediction, but how about detection? And also, the main question is, would you use the same algorithm for prediction and detection? Essentially, I assume they processing only a pre-seizure raw EEG, but yeah, just to understand why not give it everything before, after, and during seizure raw data. You know, if you're saying the data is, you know, if you can have a model that doesn't require data processing, then why not just give it everything and let the model essentially decide, you know, what window size to use, for example, and then just give it everything, including you know, before seizure, after seizure, and during seizure. What do you think of that? And the main question is also, again, just to reiterate, would you use a different algorithm for detection and prediction, or do they have to be different?
This is an excellent question that strikes at the core of designing algorithms for seizure studies, where the goals of detection and prediction often overlap but require different considerations. Let me break this down systematically. Detection versus prediction. 1. Detection. The goal is to identify a seizure as it is happening or immediately after it has occurred. Detection typically involves processing real-time EEG data or even short windows, e.g. seconds, of EEG immediately preceding or during the event. This task requires a high degree of temporal precision, as the model must recognize the onset of a seizure almost instantaneously. 2. Prediction. The goal is to forecast a seizure before it begins, ideally providing a meaningful warning window, e.g. minutes to hours. Prediction focuses on identifying pre-ictal patterns, which are subtle and can vary significantly across patients. The time horizon for prediction introduces additional complexity, as the model must balance sensitivity with the likelihood of false positives, e.g., predicting too many seizures that don't occur. Should you use the same algorithm for both? The short answer is no. Detection and prediction are fundamentally different tasks and should ideally use different algorithms or processing pipelines. Here's why. 1. Nature of the data. Detection focuses on clear and immediate seizure patterns in the EEG, often during ictal states. These patterns are typically more pronounced and easier to recognize. Prediction focuses on subtle pre-ictal patterns that occur before the seizure, often masked by noise or normal brain activity. This requires more sophisticated feature extraction or model architecture. 2. Temporal requirements. Detection operates in real time, requiring rapid processing of incoming EEG streams with minimal delay. Prediction can afford to process larger windows of data, since the goal is to forecast future events, not react to current ones. 3. Model architecture. Detection may benefit from simpler models like CNNs, which are good at recognizing spatial patterns in the EEG, e.g., high-frequency spikes during seizures. Prediction often requires temporal models like LSTMs or transformers, which are better suited for analyzing long-term dependencies and subtle temporal trends. 4. Evaluation metrics. Detection is often evaluated using metrics like latency, how quickly a seizure is detected after onset. Prediction emphasizes sensitivity and false positive rates, how many predictions are correct and how often false alarms occur. Why not use all data before, during, and after seizure? This is a valid critique of studies like the one we discussed. Here's why using all available data could be advantageous. 1. Comprehensive modeling, including all data, pre-ictal, isictal, interictal, and post-ictal, allows the model to learn the full spectrum of EEG dynamics. If the model has access to data before, during, and after a seizure, it can learn to distinguish pre-ictal patterns from ictal and post-ictal ones, understand transitions between states, which are often critical for prediction. 2. Avoiding arbitrary window selection. By restricting the input to predefined windows, e.g. 4 or 16 minutes, the model might miss important patterns that occur outside these boundaries. Letting the model decide the optimal timescale could result in more robust predictions. For example, a patient might have a unique pre-ictal pattern that starts 30 minutes before a seizure. Another patient might only show signs 2 minutes before a seizure. 3. Why this isn't commonly done. Many studies rely on predefined windows because it simplifies labeling, e.g., this window is pre-ictal, that one is interictal. Including all data requires more computational resources and might complicate training. For instance, How do you ensure the model doesn't overfit to ictal patterns when trying to predict seizures? How do you balance the dataset if ictal events are rare compared to interictal periods? What do I think of letting the model decide the window? It's a promising approach, but it would require a more sophisticated model and training process. Here's why it's a good idea. 1. Dynamic feature extraction. Instead of forcing the model to focus on fixed 10-second chunks or predefined preictal windows, you could design a model that dynamically learns which timescales are most relevant for prediction. 2. Flexibility across patients. Different patients have different seizure dynamics. A model that can adapt to individual patterns by considering all available data would likely outperform one constrained by predefined windows. 3. Technical challenges. This approach would require advanced architectures, such as transformers or attention mechanisms, which can weigh the importance of different time points in the data. It would also demand more computational power and careful tuning to avoid overfitting. Critical summary 1. Detection and prediction require different algorithms. Detection focuses on identifying seizures in real time and benefits from simpler, faster models. Prediction involves forecasting seizures based on subtle preictal patterns and often requires more complex temporal models like LSTMs. 2. Including all data is a stronger approach, letting the model learn from all available data before, during, and after seizures would likely improve both detection and prediction. This approach avoids the arbitrary constraints of predefined windows and allows the model to discover relevant patterns on its own. 3. Challenges. While more comprehensive, this approach is computationally intensive and requires careful design to ensure that the model doesn't overfit or become biased by ITAL patterns. Does this address your main question? Would you like to explore how such a comprehensive model could be designed?
I don't think you were able to convince me about using different models, and essentially it comes down to the definition of ictal and pre-ictal and ictal states. Okay, can you do rapid fire responses? I don't think you were able to convince me that using different models is essential. Does it come down to the difference between ictal and interictal states?
Yes, it largely comes down to the difference between icetal and interictal states. Detection focuses on icetal patterns, which are distinct and immediate, while prediction must identify subtle preictal patterns buried within interictal data. The complexity of preictal patterns often requires temporal models, whereas detection can rely on simpler pattern recognition techniques.
Okay, can you do very short, much shorter responses? Is that okay by you?
Of course, that's fine.
Okay, so in the pre-ictal state, we are still detecting EEG abnormality, aren't we?
Yes, but the abnormalities in the pre-ictal state are subtle and variable, unlike the clear patterns in the ictal state.
Okay, so why wouldn't we then use the same model, same algorithm to detect abnormalities in pre-ictal and ictal state? Is it just a matter of having a better model, and then essentially the ictal state becomes longer and overlapping with the intra-ictal state, and eventually the in the ictal state will essentially be gone if we can detect it accurately.
You're right conceptually. A unified model could work if it's sophisticated enough to detect gradual transitions from pre-ictal to ictal. The challenge is balancing sensitivity and specificity. Pre-ictal abnormalities are less defined, making it harder to distinguish them without flooding the model with false positives. A single model is ideal, but requires careful design to handle both states effectively.
Yeah, can you actually turn it into a standalone question? We would like to ask an expert what they think.
Sure. Here's the question. Would it be possible to use a single, highly sophisticated model to detect abnormalities across both pre-ictal and ictal states, effectively blurring the distinction between them? Could this approach eventually eliminate the need to separately define ictal states if pre-ictal detection becomes highly accurate?
Yeah, that's a perfect question. We'll go for O1 model, the reasoning model. And I can say it, should we tell it to take its time to think about it, but now just let it think as much as it needs. Yeah, surprisingly, thought about it too quickly. Few seconds evaluating detection methods. Potential unified detection model. Suggesting that if pre-ictal detection is accurate, a separate ictal detection might be redundant. That's right. I'm thinking about, yeah, it's like, I like how this, I'm thinking about this and that. How advanced deep learning models can simultaneously manage complex classifications like pre-ictal and ictal states. Let's quickly read this because this is supposedly a response. We can assume this is a response from an expert.
It is indeed possible to envision a single sophisticated model that detects abnormalities across both pre-ictal and ictal states without strictly enforcing a manual distinction between them. In practice, a modern deep learning system trained on large sets of EEG data or any other relevant biomedical signals could learn to identify a wide range of seizure-related patterns, including the subtle signs that occur shortly before a seizure. This would allow the model to operate more holistically, treating seizure onset detection as a single problem rather than dividing it into separate tasks of pre-ictal detection and ictal classification. However, it is worth noting that while this unified approach could reduce the need for separately labeling ictal states, the model would still need to learn and implicitly define what constitutes the transition between pre-ictal and ictal signals. Even if these states are not rigidly distinguished by human-designed rules, the machine would discover and utilize data features to differentiate the various stages of seizure activity. If pre-ictal detection truly becomes highly reliable, it might lessen the practical importance of detecting ictal states as a separate event, since the true clinical need would be to intervene, or at least predict, before the seizure becomes fully established. In many real-world scenarios, clinicians and researchers still find it valuable to know exactly when the ictal state begins, since interventions, reporting, and other safety protocols can differ once the seizure is in full swing. A unified model that covers the entire spectrum could indeed save time and complexity, but the decision to eliminate any explicit definition of ictal onset would depend on the clinical goals. If the highest priority is reliable and early identification of impending seizures, then de-emphasizing the exact labeling of the ictal phase might be acceptable. On the other hand, if one needs to document the precise timeline of a seizure for research or clinical treatment, a specialized classification of the seizure's phases might still hold significant value.
Well, the problem is that it sounds that the pre-ictal state, so pre-seizure state, is normally just defined by common time before seizure onset. So it doesn't sound like a very useful thing if it's predefined. And in this current paper that we were looking at, that time window is being varied from 16 to 4 minutes. So does it essentially provide evidence that it's an arbitrary time window that potentially doesn't actually mean anything? And again, if we are doing detection, then whatever we can detect, any abnormality that we can detect in the signal, it could be, we could just specify the intensity of it, or essentially like a probability of a seizure. So could we just go for, that before seizure, over time, the probability of having a seizure is increasing, linearly or potentially non-linearly. I don't think it's linear. But then we still need to find something that defines a pre-seizure time window very well. Give it to O1. That's the expert. And we also gave what the O1 said back to our original chat. That's the one, the 4O that was reviewing the paper. I'll just read its response quickly.
Your response beautifully frames the discussion.
That's the
It's
response
clear
for
that a unified model
401.
could streamline
01.
seizure detection by identifying patterns across the entire pre-ictal to ictal spectrum. The key takeaway is that clinical priorities, like early intervention versus precise documentation, will shape whether such a model eliminates ictal state definitions or retains them as a secondary output. This balance between simplicity and detail is critical when designing future systems.
And this is back to the, PhD level expert. Because I'm pretty sure 4.0 is like a master's level. A 4 or 3.5 or 4 is like an undergrad level, but yeah, 01. I don't have the feel for it yet. I haven't used it much, but yeah, I suspect it's like a PhD level. But then I have a PhD in only one very specific area, and this thing has, thousands, if not millions, of PhDs across the board level of understanding. And for the second prompt, it actually thought for longer. To begin with, it only thought for a few seconds, and on another prompt, it was thinking for a whopping 12 seconds. It's avoiding acronyms. Single page app. What are they talking about? Okay, I think it's going places. Well, it doesn't have the context of the whole conversation. Yeah, that's why we probably should have kept it as a single prompt, but now that we have that response, we might as well read it.
Defining a pre-seizure time window often feels arbitrary because it can vary widely from patient to patient, seizure to seizure, and paper to paper. Some studies define a pre-ictal period of 16 minutes, others just 4, and there is no universal agreement on what that time span should be. This discrepancy arises because there is no single set of physiological indicators that cleanly mark the exact moment when the brain shifts from an interictal, between seizures, state to a true pre-ictal, leading into a seizure state. One person might show a certain slowing or synchronization in their brain signals half an hour before the seizure starts, while another person might only display meaningful changes a few minutes or even seconds before onset. Because of this natural variability, pinning down an absolute time window can be more a matter of convention than a statement of definitive physiology. If your goal is simply to detect an oncoming seizure, it can be more practical to treat the problem as a gradual change in the probability of seizure onset over time, rather than to enforce a single, rigid definition of a preictal window. If your model is continuously assessing abnormalities in, for instance, electroencephalography data and assigning a probability of seizure occurrence within the near future, then the notion of preictal becomes less essential as a fixed label. As you move closer to the actual seizure onset, the probability could gradually or sharply rise, indicating higher risk. In a perfect scenario, the model would not suddenly snap from 0 to 100% risk at a fixed number of minutes before the seizure, but instead evolve the score continuously to reflect the level of abnormality the system observes in real time. Nevertheless, researchers and clinicians often find it helpful to define a pre-ictal period for research consistency and medical workflow. They like to measure how long before the onset the model can successfully detect warning signs, which might factor into clinical decisions about medication, patient alert systems, or caretaker interventions. Even if a continuously evolving probability is more biologically realistic, there is a practical advantage to designating a pre-ictal window for reporting and comparison across studies. Ultimately, if you are strictly focused on real-world detection and intervention, the precise boundaries of the pre-ictal period may be secondary. The most important element is the model's ability to raise an alarm when needed, regardless of whether it is 4 minutes, 16 minutes, or some other span before the seizure.
The other thing I'm curious about is that if we, even the ictal state, so if we think of it as a probability of a seizure, so then it will be just crossing whatever your 60-70% of a seizure likelihood, or potentially even, so if it's crossing like a 50% seizure likelihood, like crossing the chance level, then it should be a pre-seizure, a pre-ictal state, and once it's crossing 90%, then it should be your actual seizure going on. So should it be, does that make sense? We'll place those back into 4.0 because eventually we want to turn it into a blog or a white paper, whatever paper you want to call it, whatever color paper. It's interesting how it's praising itself. Yeah, it's 4.0 essentially praising 01. It's like, okay.
Yes, it makes sense to think of both the preictal and ictal states as intervals within a continuously evolving probability of seizure risk. If you have a model generating a moment-to-moment probability that a seizure is imminent, you could define the pre-ictal state as beginning once that probability crosses a certain threshold, for example, 50%, while the ictal classification might begin once it surpasses a higher threshold, such as 90%. This approach highlights that seizure detection is often not a hard, all or nothing event, but rather a gradual increase in the likelihood that a seizure will occur. In practice, you might want to refine how you manage these probability thresholds. you might require the model to stay above 50% for a certain duration before officially designating the signal as pre-ictal, or stay above 90% for a certain time before labeling it as ictal. Otherwise, the probability might fluctuate briefly above a threshold and trigger a false alarm. Clinically, there is also a question of how quickly and aggressively you want to respond to a rising probability of seizure. If the cost of a false positive is high, for example, if it triggers a medical intervention, you would set the thresholds higher or require that the probability remain above those cutoffs longer before taking action. Nevertheless, a continuous probability approach is indeed more flexible and biologically realistic than forcing a rigid 4-minute or 16-minute pre-ictal label. By treating seizure detection as a sliding scale, you can capture the fact that each individual may exhibit different rhythms and intensities of seizure precursors, and that these precursors can evolve gradually rather than appearing abruptly at a fixed time before seizure onset.
Yeah, so placing all that back into... Yeah, by the way, can you diagnose epilepsy better than a clinician? Yeah, that's the usual response. And that's what the 4.0 got to say about the 01. So that's what the master student got to say about the PhD student. Response.
Your point is well made. Defining a pre-ictal window is often arbitrary and varies widely due to physiological differences and study conventions. Shifting to a probabilistic approach, where the model continuously evaluates the likelihood of an oncoming seizure, aligns better with the natural variability of pre-ictal states. This dynamic method eliminates the rigidity of fixed-time windows while allowing real-time risk assessments. However, the practicality of predefined windows persists in research and clinical workflows, providing consistency in evaluating model performance and facilitating comparisons across studies. Ultimately, the focus should be on actionable and reliable alerts, regardless of the specific pre-ictal duration. This pragmatic balance ensures both biological realism and practical applicability, satisfying scientific rigor and real-world needs simultaneously. Exactly, framing pre-ictal and ictal states as thresholds within a continuously evolving probability elegantly captures the gradual nature of seizure risk. It not only adapts to individual variability, but also avoids the pitfalls of rigid time-based labels. Fine-tuning these thresholds, such as requiring sustained periods above 50 or 90%, adds robustness, reducing false alarms while ensuring clinically actionable decisions. This approach allows flexibility in balancing sensitivity and specificity, depending on the intervention's cost or urgency. By leveraging this probabilistic framework, seizure detection becomes more personalized and adaptable, reflecting the real-world dynamics of brain activity while supporting nuanced clinical workflows.
Okay, so we have to wrap up. Eventually we'll be turning this into a blog. Yeah, it seemed to be only to do with the last few points, but how about the review of the original paper as well? Maybe without mentioning any names, or yes, mentioning names. This can be done by the master's student. Yeah, might not go there. I mean, it's in the video anyway. We are live streaming, so. But yeah, wanna make the discussion more generic here. If we're just bringing it as an example, that's fine. I mean, it's gonna write it better than I ever will anyway. So if you don't think this AI can replace you at work, think again. Hey, okay, this plan looks fine. Yeah, if we can. So the NeuroVista is just an example. I'm just not sure how much we should be mentioning specific company names and stuff. Maybe we should get rid of any company names. All paper names. Yeah, it doesn't have to be specific to that paper, but we do, well, because we really trashed the paper. Yeah, maybe just not include anything specific to the paper, just turn it into a general discussion. But yes, include everything that we discussed in this entire conversation. Let's just see. We do want to link it to... Okay, it's not writing the blog already, is it? Beyond fixed window, rethinking seizure prediction and detection in EEG analysis. And we also want to... is it relevant to a rhythm scan? Actually wanted to browse. Did it browse? It didn't browse. Let's try it again. Yep, it's now in search mode. Yeah, we're doing convolutional neural net on images, on spectrogram images. So essentially feature extraction.
RhythmScan is an interactive web application designed to explore EEG data and visualize spectrograms for seizure detection using machine learning techniques. It allows users to delve into datasets, examine model performance metrics, and understand the intricacies of seizure detection models. Cite Turn Search. The platform provides access to EEG spectrograms representing both seizure and non-seizure events, facilitating the analysis of epileptic patterns. Users can navigate through individual spectrogram images, compare different datasets, and observe how models interpret these visual representations. In the Model Results section, RhythmScan displays performance metrics of convolutional neural network, CNN models trained on the EEG spectrogram data. Users can explore various configurations, assess accuracy and loss plots, examine confusion matrices, and review misclassified images to gain insights into model effectiveness and areas for improvement. By providing a hands-on experience with EEG data and machine learning models, RhythmScan serves as an educational tool for understanding seizure detection methodologies and the application of deep learning in medical diagnostics. It emphasizes the importance of data visualization and model evaluation in developing reliable seizure detection systems. For more information and to explore the application, visit the RhythmScan project page. Sign Search Uroken Soki.
Okay, let's read this quickly, but it might get messy.
Here's the revised blog outline with a reference to RhythmScan to highlight its relevance to the discussion. Title: Beyond Fixed Windows, Rethinking Seizure Prediction and Detection in EEG Analysis. Introduction. Seizure prediction and detection are vital for improving epilepsy management, offering patients more control and enabling timely interventions. However, traditional approaches rely heavily on rigid pre-ictal time windows and feature engineering, limiting their flexibility and real-world applicability. This blog explores the challenges of these frameworks and introduces dynamic, continuous models as a future-oriented solution. Additionally, tools like a bionichaus.com/rhythmscan provide valuable insights into the intricacies of seizure detection and model performance, emphasizing the role of visualization and interactive learning in advancing the field. Section 1. The problem with predefined time windows. Variability in pre-ictal states. Discuss how the variability across patients and seizures makes predefined pre-ictal windows arbitrary. For example, while some may show significant changes hours before a seizure, others might only display signs a few minutes prior. Why pre-ictal windows persist. Highlight how predefined windows, such as 4 or 16 minutes, offer consistency in research but fail to capture the complexity of evolving brain states. Tools like bionichaus.com/rhythmscan allow users to explore EEG spectrograms, offering a closer look at how patterns vary across datasets and timeframes. Section 2. Moving toward a continuous probability framework. What is a continuous probability model? Introduce the concept of assigning a moment-to-moment seizure risk probability, dynamically defining pre-ictal and ictal states based on real-time outputs. Why it's better. Flexibility adapts to individual differences in EEG signals. Biological realism reflects the gradual escalation of seizure risk. Interactive visualization. Mention how platforms like RhythmScan/bionichaus.com/rhythmscan could potentially integrate such dynamic models, helping users visualize continuous probabilities for seizure prediction. Section 3. Can one model handle both detection and prediction? Unified models for seizure analysis. Discuss the potential.
Yeah, we're having a problem of yeah, now it started the canvas, so it won't be doing anything in the chat. The advantage is that we can edit the canvas directly. The disadvantage is that the text to speech would not work anymore. Yeah, so the question, if we are doing just a review for the paper, no, we don't want to do a review for the paper. That's the video is there for, might have it as a standalone video. I mean, the video will have a transcript, so we could just, well, the transcript is in ChatGPT. Anyway, going places now. Anyway, eventually a blog like this will be available on the website. So stay tuned. Don't forget to check out the site. And I'll see you next time. Bye.